magnetic field. So here that may align or not align. Align, that means align parallel or anti-parallel with the external applied magnetic field. Now any other orientation is not possible or not permissible. Similarly, for I equals to 1, 3 by 2 and 2, the number of possible orientations, if the value of I equals to 1, then the number of possible orientations will be equals to 2 into 1 plus 1, that is equals to 3. And similarly, if the if the value of I will be 3 by 2, then the number of possible orientations will be 2 into 3 by 2 plus 1, that is equals to 4. And similarly, if the value of I will be 2, then the number of possible orientations will be 2 into 2 plus 1, that is equals to 5. Then the different orientations of a nuclear magnetic moment for the nuclei are associated with different energies. So the energies being equals to minus mi gn mu b0, where b0 is the strength of the applied magnetic field, and the energy levels for I equals to half can be shown as, if the value of I equals to half, then it will have two orientations and the two energy levels. So the first energy level, that is E alpha, equals to minus half gn mu n b0, and the second energy level having E beta, that is equals to half gn mu n b0. So here, so these are the energy level corresponds to the mi value equals to plus half. If the value of the mi will be plus half, so here the value of the mi will be plus half, then having lower energy level, and if the value of mi equals to minus half, that is the beta state with upper energy level, and the energy of separation between the lower and upper energy level. So this is the separation between the lower and upper energy level, del E equal to Gn mu n B0. Because the E alpha, the value of E alpha equals to minus half Gn mu n B0, the value of E beta equals to half Gn mu n B0, and hence the energy difference between the lower level and upper level, that is del E equals to Gn mu n B0. And the energy level with m value equals to half is denoted as alpha, and sometimes described as the spin off, and the state with m equals to minus half is denoted as beta and is described as spin down. For the nuclei we are interested in, it is the alpha state, which is the state of lower energy state, and the difference of energy that already we have discussed, that the energy difference between the lower and upper energy state equals to Gn mu n B0. This implies that the frequency of the radiation, if you calculate the frequency from the energy difference, that is nu equals to Gn mu n B0 by h. So for magnetic fields used in the NMR instrument, this frequency falls in the radio frequency region of the spectrum. In other words, a suitably radio frequency radiation can bring about the transition of the nucleus spin from alpha to beta state. Now coming to the population of energy levels. So the population of energy levels is governed by the Boltzmann distribution law. Already we have studied the Boltzmann distribution law many times. So here N2 upper divided by N1 lower, that means the number of spins in the upper state divided by the number of spins in the lower state equals to e to the power minus del E by kt, where del E is the energy difference between the two energy levels, and k is the Boltzmann constant having the value 1.38 into 10 to the power minus 23 joule per Kelvin. As the energy difference between the two spin states is very small, the upper level will always appreciably populated all the temperature above absolute zero. And now let us calculate the ratio of the protons in the magnetic field 1.5 Tesla at room temperature. So here del E value equals to Gn mu n B0, and for a proton the value of Gn already that is mentioned 5.585, and the value of mu n that is 5.05, and b0 is the value of mu n equals to 5.05 into 10 to the power minus 27 joule per Kelvin, and the value of b0 is given, that is 1.5 Tesla. So putting all these values, we can calculate the daily value equals to 4.23 into 10 to the power minus 26 joule. Since the daily by kT is very small, e to the power minus daily by kT may be approximately equal to 1 minus daily by kT. Thus, the ratio of nuclear spin populated in two energy levels will be 0.9999898. That means the ratio of populated, the number of populations of the two energy level will be approximately same. Since the transition from the lower state to the upper state involves the absorption of radiation, and that from the higher state to the lower state, the emission of radiation, no absorption can occur unless the lower energy level has excess of protons. So, in the above given example, it is found that the lower energy level has about 2 excess of spins for every. So, from this value, we can say that the lower energy level have about 2 excess spins for every 10 to the power 5 spins in the upper level. So, that means if 10 to the power 5 spins will be in the upper level, then 10 to the power 5 plus 2 spins will be in the lower level. Thus, it is a very small number but is finite, and hence the absorption is observed, and in the absence of this small excess of population, no NMR can be observed. So only two excess of populations are there in the lower energy level, that's why NMR will be observed. But if the number of spins will be same, then no NMR will be observed. Now coming to the Larmor precession. So in order to understand the phenomenon of Larmor precession, you should recall the behavior of a spinning top, or that is a gyroscope. You know that the spinning top executes two simultaneous motions. So this is the diagram of a spinning top. So that will execute two simultaneous motions. One of the motion is like this. This is the one motion, and the other motion, that will rotate around its own axis. So it spins on its axis as well as around its axis. So that means two simultaneous motions will take place for a spinning top or for a gyroscope. The motion around the vertical axis arises due to interaction of spin, that is the gyroscopic motion, with earth gravity acting vertically downward. This motion is called precessional motion, and the spinning top is said to be precessing around the vertical axis of the earth gravitational field as shown in this figure. So, a spinning nucleus or spinning proton, when placed in an external magnetic field, that will also exhibit a precessional motion. A spinning nucleus under the presence of external magnetic field can precess around the axis of an external magnetic field in two ways. That means it can either align with the field, and the spin in which the motion in which it will align with the field that will present in the lower energy state, or it can opposite to the field direction, so that will present in the higher energy state. So you can see, so this is the spin motion. So for this spin motion, according to rule, you can see the internal magnetic moment will be in this direction, and here this is the external magnetic field B0. So both having same direction, so that's why that is aligned with the external magnetic field, and hence that will present in the lower energy state. And similarly, if the spin motion will be like this, then its magnetic moment, then its internal magnetic moment will opposite to the external magnetic field, and that's why that will present in the high energy level. So the precessional frequency omega is called a Larmor frequency, that is directly proportional to strength of the external magnetic field B0. That is, omega is directly proportional to B0, or omega equals to some constant gamma into B0. So here gamma is called magnetogyric or gyromagnetic ratio. It is the ratio of the nuclear magnetic moment mu and the nuclear angular momentum I. So that is gamma equals to mu by I, and the normal frequency nu and the precessional frequency omega can be represented as here omega equals to 2 pi nu equals to gamma into B0, or nu equals to, from this equation we can write nu equals to gamma B0 by 2 pi, that is equals to B0 by 2 pi, which is constant, into nu by I. After substituting the value of I and nu from equation 1 and 3 already we have solved, we can find that the frequency value nu equals to Gn mu n B0 by h. Now coming to the mechanism of resonance. There are two different ways of achieving the resonance. To understand this, let us look at the diagram number 5. So here the diagram 12.5 again. This one, this diagram, precessional motion diagram. So the equation shows that there are two variable parameters. So here this is the equation. From this equation you can see two variable parameters are there. So the two variable parameters are frequency nu, and the two variable parameters are frequency nu and external magnetic field B0, and Gn, mu n, h are being constant. One obvious way to achieve the resonance is to vary the frequency at a fixed magnetic field strength. So that means two variable parameters are there. One is frequency nu and the other one is magnetic field, external magnetic field B0. So the two ways to get, out of the two ways to get resonance, the first way to achieve the resonance is to vary the frequency at a fixed magnetic field strength. This technique is called frequency sweep method. That means magnetic field strength will be fixed and frequency will be varied. In this method, the sample is placed between the poles of the strong magnet, which generates two energy levels that cause the nucleus to undergo precessional motion, and the sample is then irradiated with a variable radio frequency generated by oscillator and transmitter, and the resonance condition is achieved when the frequency of the radio frequency radiation matches with the Larmor precessional frequency. Under this condition, that is called resonance, the nuclei of the lower spin state absorb the radiation and go up into the higher spin state, and the transition is commonly known as spin flip. So here, alternatively, we can keep the oscillator frequency constant. That means frequency will be constant and vary the so the second way to get the resonance, we have to keep the frequency constant and vary the magnetic field strength. This technique is called field sweep method. So when field strength is low, the precessional frequency is lower than the applied radio frequency, and since two frequencies do not match, no energy is absorbed. As we increase the field strength, the precessional frequency start increasing, and at a certain field strength, it will match exactly with the applied radio frequency, and hence at that situation, resonance condition is achieved and radiation is observed. So when the radiation will be observed, that causes transition from the alpha to beta state and so on. In the common instrument, both the methods are used, both the field sweep method and frequency sweep method. So first one is frequency sweep method and the second one is field sweep method. So in common instrument, both the field frequency sweep method and field sweep methods are used. but both the methods are used. However, the field sweep method is preferred. It is because the relatively so it is because the field sweep method is comparatively easy to varying the field. So in the field sweep spectrometer, the continuous variation of magnetic field strength is achieved with the help of special coil present in the poles and the magnet. So that means we have to in the commonly used NMR instrument, the frequency will be constant and the magnetic field will be varied. So when magnetic field will be varied at a particular position, the precessional frequency match with the constant frequency, and in that condition resonance will happen, and hence at this situation the transition from the alpha to beta state will occur. In both the setup, the proton are brought into the resonance one by continuously varying either the field or frequency. Therefore, this is called continuous wave spectrometry. The CW method was basis of all NMR instrument constructed up to above at the end of 1960. Though the continuous wave method CW method is still used in smaller is still used some low resolution instrument, but the modern instrument use fault Fourier transfer, that is FTNMR. So now coming to the relaxation mechanism. So the population of the energy level is governed by the Boltzmann distribution law, as we have discussed already. Once the radiation is observed, the population distribution gets disturbed. As the population difference between the two spin states is very small, the population of the lower and higher energy level would become equal, and after absorption of radiation sometimes, it means that the resonance signal has achieved saturation and no more energy can be absorbed. So initially, the population of the lower energy level will be slightly greater than the population of the higher energy level, as we have already discussed that for a proton, the for if 10 to the power 5 population will be there in the higher energy level, then for the lower energy level, the population will be 10 to the power 5 plus 2. So as the number of the populations, as the population difference between the two spin states is very small, that is approximately 2 for the proton, the population of lower and higher energy level become equal after absorption of radiation after some times. So when the population of the two energy states will be equal, after that it will get saturated and no more energy will be absorbed. However, there are some competitive phenomena that do not allow the stage to cope. This is called relaxation mechanism. In this process, relaxation of nuclear spin in the excited state relax down to the lower state, though radiation less process. There are two types of relaxation mechanisms are there. The first one is spin lattice relaxation, and the second one is spin relaxation. So now first we will discuss the spin lattice relaxation. This process involves transfer of energy from the nuclear spin of higher energy state to the molecular lattice, and the random motion of the adjacent nuclei of the lattice set of fluctuating magnetic fields at the nucleus, leading to its interaction with the magnetic dipole with excited nucleus. This results in transfer of some of its energy to the neighboring atoms. This is also called a longitudinal relaxation, and thus the nucleus return to original low energy state, and hence the population of the low energy level will again increase, and that will again absorb energy, and the resonance condition will continue. And the second type of relaxation, that is called spin relaxation. This mechanism of involve mutual exchange of spins of the two preceding nuclei in close proximity with each other. For example, if there are two nuclei, then one of the nucleus can flip down and the other may flip up by mutual exchange of spins. This is also called transverse relaxation. Spin relaxation is also called transverse relaxation. It shortens the lifetimes of an individual nucleus in the higher state but it does not contribute to maintenance in the required excess of lower energy state. Due to the relaxation mechanism, the excited state have small lifetimes. So here we will discuss nuclei other than protons. As we have already discussed that those nuclei show NMR, only those nuclei show NMR that have nuclear spin angular momentum I is greater than equals to half. That means having some positive I value. More than 200 isotopes in the principle can be studied by NMR. Of course, 6 carbon 13, 9 chlorine 19, 15 phosphorus 31 are most widely used besides proton. So the commonly used nucleus is proton NMR, that is called PNMR. Apart from this PNMR, CNMR, that is carbon NMR, FNMR, chlorine NMR, and phosphorus NMR are also possible. The characteristics of these nuclei are given in table number 1. So here the nucleus spin angular momentum I, and here the value of I is half for proton, and for 6 carbon 13 the value is also half, for 9 chlorine 19 the value is also half, for 15 phosphorus 13 31 the value of I is also half. So, and these nuclei are used for NMR study. Now coming to the Fourier transfer NMR. The intensity of NMR signal is proportional to concentration of the observing species. Many times we come across the situation where the amount of sample available for the analysis is very small, especially in case of biological samples. So in such cases, signal to noise ratio is very small and it becomes difficult to distinguish the signal from the background noise. And a way out to scan the sample number of times and add different scans with the help of a computer. So in this process, the signal being at the same frequency every time adds up, where the noise becomes random in the nature gets cancelled out. So this involves the signal to the noise ratio. However, taking a number of scan, it is quite sometimes uh, 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 it is quite time consuming. For example, if one scan if one scan can be completed in about 1 minute, it will need more than an hour to record the meaningful spectrum. And so that means for traditional normal NMR, as the intensity of the so when the concentration of the sample or the amount of the sample will be very less, that is particularly for biological samples, in that case, the signal to noise ratio is very small. That means we cannot analyze the signal because the intensity of the signal and noise that will match with one another. And hence, so in order to get a specific signal, we have to run the scan number of times. So that's why for this, the time of the analysis for one sample that will more than 1 hour will be consumed to record a meaningful spectrum. And in order to avoid this type of problem, the Fourier transformation FTNMR is used. The FTNMR spectroscopy is generally concept used to study very weak signal after isolating it from the environmental noise. Now coming to very important part, that is definitely question will come, that is called chemical shift. The description of the behavior of the nuclei present in the magnetic field discussed so far holds good only for bare nuclei, because all that we have discussed, that is the magnetic all the magnetic spin generation of magnetic field that we have discussed, that is for bare nuclei. But in actual case, bare nuclei will not possible because the nuclei will associated with electrons. So the resonance condition for the nuclei, that is nu equals to Gn mu n B0 by H. It implies that all the nuclei for a given type in a sample should absorb energy corresponding to above nu value. And if this case, if This was the case, the NMR spectroscopy would have been no use to the chemist because in the real system we do not deal with bare nuclei. So the nuclei are surrounded by electrons and and their presence can modify the field experience by the nuclei of the shielding and de-shielding them. So this makes the nuclei to come to the resonance at different frequencies. So let us discuss in details. The electrons circulating around, so because all the theory we have discussed till now that is applicable for bare nuclei, but in actual case the possibility of bare nuclei is so the analysis of bare nuclei is impossible because every nuclei, because electrons are circulating around the nucleus. So let us consider the case of hydrogen atom. So in case of hydrogen atom, that is in a electron is circulating around the nucleus in a spherical fashion that produces induced magnetic field, that is B induced, which oppose the applied field B0. Therefore, the magnetic field experienced by the proton in a molecule placed in a magnetic field strength B0 is always less due to shielding and screening of the nucleus by the surrounding electrons. So that means every nucleus is surrounded by electrons, and the electrons will produce induced magnetic field that is opposing, that is in opposite direction with the external magnetic field B0, and hence the nucleus will feel lesser magnetic field than B0. So here B0 is the field strength of the applied magnetic field, but the nucleus cannot feel B0 amount of field strength. So due to this screening or shielding of electrons around the nucleus. So the effective magnetic field experienced by the nucleus, that is B effective, can be given as B effective equals to B0 minus B induced. So the induced field, on the other hand, is proportional to the applied field, that is given by the expression B induced is directly proportional to B0. So B induced equals to sigma into B0. So the proportionality constant sigma is called shielding constant, and that is a measure of extent of shielding by the nucleus, shielding of the nucleus by the electrons. Now substituting the value of B induced, we can write B effective equals to B0 minus sigma B0, that is equals to B0 into 1 minus sigma. Thus, the presence of extranuclear electronic environment, the resonance condition get modified as, so for bare nucleus the resonance condition, as we have discussed that for bare nucleus the resonance condition nu equals to Gn mu n B0 by H, but due to presence of electrons circulating around the nucleus, the actual resonance condition, that is nu equals to Gn mu n B0 into 1 minus whole into 1 minus sigma divided by H. So in a molecular system containing nuclei other than hydrogen, pi or conjugated electrons, the field generated by the electrons may augment with the applied field, and this is effective, and that is the effective field nucleus may be more than the applied field. So the value of sigma will be negative. In such case, we say that the nucleus is de-shielded. So that means for molecules having pi electrons or conjugated electrons, so in that case, the induced magnetic field will be positive, or will be same, will be aligned to the applied magnetic field. So in that case, the nuclear will be said to be de-shielded. So when shielding occur, B effective is less than B0, hence B0 must be increased to bring the nucleus to resonance. On the other hand, when de-shielding occur, B effective is more than B0, requiring the field to be reduced to achieve the resonance. Thus, nucleus comes in the resonance at lower field. Therefore, due to shielding, identical nuclei have different chemical environments, resonate at different values of the frequency or applied field. So these being the characteristics of the chemical environment that can be used to identify the various type of environment in which the proton is present. Since the shift in the position of the resonance is due to difference in the chemical environment, it is called chemical shift. Now coming to first, we'll discuss the shielding mechanism. The magnitude of the chemical shift is proportional to the strength of the magnetic field generated by circulation of surrounding electron about the proton. In other words, to understand the chemical shift value originating from the structural arrangement, it is essential to understand the nature of the electron circulating corresponding to the induced magnetic field. So, the protons experiencing shielding due to combination of different types of electronic circulations. It may be noted that electronic transition of a free hydrogen atom and hydride ion are spherically symmetrical. The applied magnet. So here the electronic transition of free hydrogen atom or hydride ion that is considered to be spherical symmetrical. You can see the applied magnetic field induces electronic circulation around the nucleus in place of perpendicular to the applied magnetic field. So this generates a small magnetic field which is which is in the neighborhood of the nucleus, but that is opposed to the direction of the applied magnetic field as shown in the figure. So this is the direction of the applied magnetic field. You can see this is the direction of the applied magnetic field, but the induced magnetic field, so this is the direction of induced magnetic field, but the induced magnetic field due to the circulation of electron around the nucleus is in opposite direction to the applied magnetic field. So this is called diamagnetic effect and cause the resonance to be observed at higher field. So that means the nucleus will be shielded. So here this is the nucleus and this is the direction of circulation of electron around the nucleus. So the nucleus will be shielded, and as the nucleus will be shielded, the phenomenon of resonance can be observed at higher field than V0. In organic molecule where hydrogen is bound to carbon and other atoms, the electron distribution is not spherical in the above case. So for hydrogen atom or hydride ion, the electron distribution is spherical. But in case of organic molecule where carbon and other atoms will be there, the electron distribution is not spherical. So the electron occupy p and d orbitals in addition to that of the s orbital. So in such case, two types of effects are generated. These are diamagnetic effect in which the induced magnetic field direction is opposite to the applied magnetic field, and in case of and in that case the electronic motion will shield the nucleus, and the other kind of effect is paramagnetic effect, which is arises due to the induced magnetic field whose direction is parallel to the applied magnetic field. So this effect is called de-shielding of the nucleus. Now coming to standard chemical shift. As already we have discussed that the NMR of bare nuclei cannot be possible. We do not have reference to measure a chemical shift. So therefore, we need to some reference standard with respect to which is extend the shielding and de-shielding of the external field versus the chemical environment can be measured. So this is very similar to choice a standard hydrogen electrode are the reference for defining the electrode potential of the half cells in the electrochemistry. So in the similar way, in case of organic compound, generally tetramethylsilane, that is CH3 whole 4 Si, that is called tetramethylsilane or TMS, is used as a standard with respect to the chemical shift data reported. The TMS have the following characteristics. That's why that make the molecule to choice as a reference. So these are the characteristics of the TMS. So that's why TMS tetramethylsilane is used as a reference material for measuring the chemical shift. So the first one is it gives a strong and sharp signal at very high field. Therefore, it does not interfere with the signals of all other type of protons in different organic molecules as they observe at lower field relative to the TMS. All the 12 protons are chemically and magnetically equivalent. Therefore, this gives a reasonably intense signal even at low concentrations. It has low boiling point and is soluble in most organic solvent. Hence, it can be easily removed and separated from the organic compound and solvent after the spectrum is recorded. So it is highly inert and do not react with most of the organic compounds. Hence, it does not interfere with the NMR measurement. So due to these four important properties, tetramethylsilane is used as a reference material for measure or standard material for measurement of the chemical shift. Now coming to unit of chemical shift. So in NMR, the x-axis According to the principle, the x-axis represents the frequency of radiation being absorbed or the field at which the resonance is achieved for a predetermined radio frequency. That means two types of two mechanisms are there. If the frequency will be constant, then x-axis will be magnetic field, and if the field will be constant, then the x-axis represent the resonance frequency. However, using the frequency or field is quite inconvenient. So the frequency of the absorption depends upon the applied field. So the position of the signals of a given analyte would depend upon the applied field. Analyte means the sample under investigation. So that is the position of the signal obtained for a given analyte on the different instrument would be different. Therefore, we need a parameter that is independent of the applied field. Such parameter is called delta or ppm, which is a dimensionless quantity. Now let us try to understand the meaning of delta or chemical shift. So here TMS used as the magnetic field. So first, suppose we measure the test sample, that is the reference or standard sample, that is the TMS, using same magnetic field B0. So the resonance condition of the two would be given as, so H nu test. Test means when TMS sample will be there. So H nu test equals to Gn mu n B0 whole into 1 minus delta mu test. Similarly, H nu TMS is the standard one. So in that case, H nu TMS equals to Gn mu n B0 whole into 1 minus sigma TMS. And similarly, for your test sample, H nu test equal to Gn mu n B0 whole into 1 minus sigma test. And the shift in the resonance frequency can be given as H nu test minus H nu TMS, that is equals to Gn mu n B0 whole into 1 minus sigma test minus Gn mu n B0 into 1 whole into 1 minus sigma TMS. So that is H whole into nu test minus nu TMS equals to Gn mu n B0 whole into 1 minus sigma test minus 1 minus sigma TMS. So that is equals to nu test minus nu TMS equals to, so this 1 will be cancelled, and finally you will get minus sigma test plus sigma TMS, and the value of sigma TMS will be 0. Hence we can write nu test minus nu TMS equals to Gn mu n B0 whole into minus sigma test by H. Suppose we measure two samples, test and TMS, at a double field. So that means if the applied field will be doubled, then in that case only you have to multiply 2 here. That means the applied. So in this case the applied field will be B0. In the second case the applied field will be double, and we will get this value. So that is the frequency difference between the test and reference signals get doubles. Since the shift in resonance position is due to chemical environment, this must be independent of the applied field. So this can be achieved by dividing the shift in the field or shift in the frequency by respective spectrometer field or frequency. That means which is equals to nu test by nu TMS divided by nu operating frequency, that is nu OP. So nu OP is the operating frequency of the spectrometer. Now this makes the shift dimensionless, but the problem still remains, and the value of the ratio is very small, because shift in the field or frequency is nearly 10 to the power 6 times smaller than the measuring field frequency. Therefore we have to multiply this dimensionless quantity by 10 to the power 6, and hence the chemical shift delta is mathematically expressed as delta equals to nu test minus nu TMS divided by operating frequency nu OP into 10 to the power 6. So usually the delta scale ranges from 0 to 12 ppm. At a higher value of delta implies the signal to be more downfield from the reference, where high field strength will correspond to a lower delta value. In order to solve this problem, another scale, that is called a tau scale, has been proposed and where tau equals to 10 minus delta. So here this is the delta scale. The lower one is the delta scale. So in the delta scale, so here the delta value increases from right to left and the tau value increases from left to right. So the TMS is arbitrarily assigned to 10 tau and the unit of the 10 tau, so that is applied as 10 tau. So this the unit is still in ppm and only difference in the scale. And here in the figure that is given the range of chemical shift value for different types of protons. So here this is the chemical shift value of if methyl CH3 CH2 CH. For this type of proton the chemical shift value will fall in this range 0 to 1 ppm, and for CH, if the carbon is attached to nitrogen, sulfur, then or aromatic ring, nitrogen, sulfur or aromatic ring, its sigma value will fall within 2 to 3 ppm. And if the carbon is attached to halogen atom or oxygen atom, that will fall just above 4. And if one double bond will be there, that will fall near 6. And if aromatic hydrogen will be there, that will for 7 to 8. For aldehydic group, for aldehydic proton, that is 9 to 10. For carboxylic acid, that is 10 to 12. So these are the different range of chemical shift values for different types of protons. Now coming to factors affecting chemical shift. First is electronegativity. We know that the atom with higher electronegative value in a molecule draws electron density towards itself, and this causes a decrease in electron density leading to deshielding of the nucleus. Thus, increasing the electronegativity, delta value will become higher and that will go downfield. For example, presence of hydrogen atom in for CH3F, the delta value will become 4.26. But in case of methane, the delta value is 0.23. But when one of the hydrogen atom will be replaced by fluorine atom to form chloromethane, in that case the delta value of the proton will become 4.26. Similarly, for chlorine, CH3Cl, here the delta value will be 3.10. And for CH3Br, the delta value will be 2.65. For CH3I, the delta value or chemical shift value will be 2.10. So that means increasing electronegativity shifts the chemical shift increasing electronegativity, the chemical shift value will become higher and the proton will go downhill. So the data shows that effect of increasing electron withdrawing on the chemical shift of the remaining proton is cumulative, but that is not additive. So now coming to anisotropy of the chemical bonds. So the chemical shift is dependent upon the orientation of the NMR active nucleus with respect to neighboring bonds, especially pi bonds. So in such cases, circular motions of the pi electron in presence of the applied magnetic field generates induced magnetic field, which is anisotropic in nature. Anisotropic means that is some part of the molecule will in some part of the molecule the field will oppose the applied magnetic field, while in other part of the molecule that will align with the applied magnetic field. So let us understand this situation by taking one example of a carbonyl group. So in the carbonyl group, due to presence of this pi electron, so this is the shielding region and this region is the de-shielding region. So these are the de-shielding regions. So there are two cones. There are two cone-shaped volumes that is applied, that is parallel to the C double bond axis. So these are the de-shielding regions, and any proton falling on this region would come to resonate at low field and that having higher delta value. So here one proton is there, due to this de-shielding region that will resonance, that will get resonance at low field and having high value of delta. So the high chemical shift around 9.2 ppm for the Aldehyde proton is typically examples of this case. So now we'll take 3-4 minutes of break. After that again we will continue. So here we will continue. The other factor, so here we have discussed the factors affecting chemical shift. The first one we have discussed, that is electronegativity. The second one is anisotropy of chemical bonds, and the next one, that is the presence of hydrogen bonds. In case of hydrogen bonding, the hydrogen atom is shared by two electronegative atoms. It is highly deshielded and the resonance occur at low field, and correspondingly high value of delta will be observed. So in case of alcohols, amines and thiols, this type of varying degree of so due to varying degree of hydrogen bondings, the resonance occurs at low field and having corresponding high value of delta. Now coming to spin-spin coupling. Under low resolution, that is at low fields, we generally get many signals in the NMR spectrum as the different types of protons in the molecule. Then the ratio of intensities of the NMR signal is measured by the area under the peak measured. So the ratio of intensity of the NMR signal is measured by the area under the peak is measured by area under the peak is a measure of the number of protons in each group. However, at high resolution, spectral bands of a molecule containing non-equivalent protons are split into two or more components depending upon the nature of the neighboring groups, and the splitting of the signal is due to the interaction of nuclear spins of adjacent nuclei and the phenomenon causing such type of splitting of signal, that is called spin-spin coupling. The interactions of coupling of the interaction or the coupling of the spin is through bonding electrons. So this effect is normally not observed if the coupled protons are more than 3 sigma bonds away. So that means if the coupled proton will be at a distance more than 3 sigma bond, the coupling will not observe. But when the coupling protons will present near the observed proton, then spin-spin coupling will taking place. So this effect is normally not observed if the coupled protons are more than 3 sigma bonds away. The splitting pattern of different signals can provide very important structural information. Now let us learn about taking a particular example of ethyl chloride. So, under the condition of low resolution, ethyl chloride show two signals in the NMR spectrum. One is for CH3 and another for CH2 protons. So, ethyl chloride is so the formula of ethyl chloride is CH3 CH2 Cl. So if low applied field will be there, that means under the condition of low resolution, two types of protons will be there. So this is one NMR peak will come for this proton, and another NMR peak will come for CH2 type of protons. So when under the condition of low resolution, the ethyl chloride show two signals in its NMR spectrum. One is corresponding to, so the first corresponding to the CH3 type of proton and the other corresponding to the CH2 type of the proton. And the peak area are in the ratio of 3:2. Because here 3 protons are there, here 2 protons are there. So the peak area of the two peaks will be 3:2. When the same spectrum is recorded with a high resolution spectrometer, the CH3 observation, the CH3 split into 3 lines, that is called a triplet, and the CH2 absorption band split into 4 lines, that is called a quadret. This splitting can be explained in terms of change in magnetic field experienced by the proton of one group due to the possible spin arrangement of the protons in the adjacent group. Now let us focus on the focus our attention on the methyl protons, that is the CH3 protons of the ethyl chloride. Now in the absence of neighboring methylene group, so here we will concentrate our, so here first we will focus for this CH3 type of proton. If this CH2 group will absence, if suppose this CH2 group will absence, then In the absence of the neighboring methylene group or CH2 group, protons, methylene group protons, that is CH2 group, the methyl proton, that is CH3 group, would come to resonance at a certain frequency depending upon the effective field strength experienced by them. It will give a single signal in the low resolution spectrum. But in the presence of the methylene group with two equivalent protons, the field experienced by the methyl proton get altered because the nuclear spin of the methylene proton also acts as a bar magnet, and the magnitude of effect would depend upon the relative orientations of the nuclear spin of these two protons, and hence the nuclear spin of the two protons can have four possible combinations. So the nuclear spin of the two protons means the CH2 protons having different set of combinations. The first one is that may align with the first case, the two combinations. In the first combination, both the spins are in alpha state. So here in the first combination, both the spins are in alpha state. So these are in alpha state. So all these are aligned with the direction of the applied field. This should augment the magnetic field experienced by the methyl protons. As a consequence, the methyl proton would come to resonance at a lower field than that of the absence of the methylene proton. Similarly, the first combination is that alpha state means the two CH2 protons will align with the external magnetic field, and the other case, so four combinations will be there. The first one is the CH3 proton will oppose to the magnetic field, and the CH2 proton will align to the magnetic field. And the second combination, the CH3 proton will oppose to the magnetic field, and the CH2 proton will oppose to the magnetic field. And the next combination, the CH3 proton will align with magnetic field, and the CH2 protons will align with magnetic field. So, and the third combination will arise when the CH3 proton aligned with magnetic field, but the CH2 proton opposed with magnetic field. So, as a consequence, the methyl proton would come to resonance at a lower field than in the absence of the methylene proton. Similarly, the fourth combination, in which both the spins are in beta state, would make the methyl group proton to come to resonance at a higher field. The other two combinations with one alpha and one beta spins would have no effect on the methyl protons absorption. Therefore, the resonance of the absorption signal of the methyl protons would be split into three peaks, that is in a triplet within the ratio of 1 is to 2 is to 1. And similarly, in the same way, if we focus on the methylene proton, that means the CH2 proton, and look for the possible spin combination of the methyl group protons, we will find there are 8 such combinations. As you notice, these combinations fall under 4 groups. Then accordingly, the methylene proton signal split into 4 lines that will show a quadrate and having intensity ratio 1 is to 3 is to 3 is to 1. Similarly, we can take other examples of the molecules in which the given type of proton has one or two or three or more equivalent neighboring protons. It has been found that the number of lines in a signal is governed by n plus 1 rule. That is, a given signal would split into n plus 1 lines where n number of equivalent protons on the adjacent carbon atoms. And in such cases, the intensity ratio can be governed by the Pascal triangle. You can see, so this is the Pascal triangle, so which is given by the coefficient in terms of the expansion 1 plus x to the power n. So the separation of this fixed frequency is called coupling constant. So this separation, that is called peak. So peak frequency, that is called coupling constant. It is denoted by J and is a measure of the strength of the coupling interaction. The coupling constant is dependent upon the strength of the applied magnetic field. This is the simple rule for determination of multiplicity or spin-spin interaction of the adjacent group hold only in case where the separation of the regional lines of the interacting group delta is much larger than the coupling constant J. So that is delta should be much larger than J. If delta equals to J, then the simple rule of multiplicity no longer hold good. So now we will discuss the magnitude of coupling constant. So here, the first one is magnitude of different types of spin-spin coupling constant for protons. So here, if geminal proton is there, geminal proton means the two protons will attach to a single carbon atom. So here, the value of the coupling constant is in the unit of hertz, that is 10 to 18, depending upon the electronegativity of the attached group. And for vicinal protons, and that depends upon the dihedral angle. And here, if the two geminal protons are attached to a double bonded carbon, and the J value will be in the range of 1 to 4. And similarly, if the two vicinal protons attached to double bonded carbon atom with cis configuration, that is 5 to 14. And for trans configuration, that is 11 to 19. And here, if the first proton is attached to a carbon atom and the other proton to the adjacent carbon atom, which is a double bonded carbon atom having the value 4 to 10. And this type of cis or trans group having the value 0 to 2. And here, for this type of group having the value 10 to 13. And if this is the proton under observation, and if for the orthoproton, its J value will be 7 to 10. For meta, its J value will be 2 to 3. For paraproton, it will be around 0 to 1. Now coming to the instrumentation for the NMR spectroscopy. So the essential component of the NMR instrument contains a highly stable magnet, sample probe, source of the radio frequency radiation, phase sensitive detector, data processing unit. And here this is the schematic diagram of a NMR spectrometer showing the various components. So these are the two magnets, and here so radio frequency oscillator is there that will produce the radio frequency, and inside the sample tube, the sample under investigation will be there here inside the tube, and this is the amplifier, and this is the recording device. So the first one is magnet. Typically, in all type of NMR spectrometer, the sensitivity and resolution of a spectrometer critically depends upon the strength and quality of the magnet. Since the sensitivity and resolution both increase with increase in field strength, it is advantageous to operate the instrument at higher possible field strength. In addition, the field must be homogeneous, uniform, and reproducible. Three types of magnet have been used in the NMR spectrometer. These are permanent magnet, electromagnet, superconducting, solenoid magnet. The permanent magnet with strength that need an oscillation frequency less than 100 megahertz for bare protons have been used for commercially continuous wave spectrometers. So these are very temperature sensitive and require expensive cooling and shielding. However, these are not ideal for extended period and for data accumulation because the field drift problem. And the next one is the electromagnet. So now the rarely used in the NMR instrument. So the modern high resolution spectrometers are superconducting magnet of temperature or of 1 Tesla or above, superconducting magnet or 1 Tesla or above. So these are the simple, small size and produce high field strength because having low operating cost. Now coming to the sample proof. It is a key component of the NMR spectrometer which is not only hold the sample in a fixed position in the magnetic field but also contains an air turbine to rotate the sample. The sample is spin so as to ensure experience uniform field. In addition to this, it houses a coil for generating radio frequency. So according to this diagram, so one coil is around the sample tube that produces the radio frequency, for excitation and also for the detection of the NMR signal. The earlier NMR spectrometer uses to have separated transmitter and receiver coils perpendicular to each other for excitation and pulse detection of the signal. But for the modern spectrometer contains a signal coil probe which is sweep mode and a fixed frequency is generated from the radio frequency generator and the frequency sensitizer. The spectrometer is known by operating frequency of 60 MHz, 100 megahertz or 500 megahertz instrument and so on. However, the FTNMR, the sample is irradiated with a pulse containing a range of the frequency sufficiently greater to excite the nucleus having different resonance frequency. Now coming to the detector. So the detector, and this is about the sample handling. For the sample handling, the most commonly used solvents are deuterated chloroform, that is CTCH3, deuterated benzene, that means the no protons will be there, that should present 1H2, that is called a deuterium should be present, because we know that in chloroform CHCl3, if the solvent contains a proton, then that will interact with the proton protons of the sample under investigation. So these solvents, so the commonly used solvents are deuterated chloroform CdCl3, that means that is having no proton, deuterated benzene, that is C6 D6 having no proton, deuterated acetone CT3 COCD3, that means in place of hydrogen atom deuterium should be there, deuterium nucleus should be there, and similarly deuterated dimethyl sulfoxide. So this is the representation of the NMR. In the x-axis you will find the chemical shift and y-axis represent the intensity. Now application of NMR spectroscopy. For quantitative application, so the NMR spectrum has a unique feature directly proportional to between the peak area and the number of nuclei responsible for that peak. Unlike other spectroscopic technique where a calibration plot is prepared using pure compound varying the concentration, but here calibration curve is not so required. Now, thus, if an identifiable peak for one constituent of the sample do not overlap with the other constituent peaks, the area of these peaks can be used to establish the concentration of the species directly provided and the signal area per proton is known. So here standard sample. So here calibration curve is not so required. From the area of the peak, we can measure the concentration. Some example of quantitative determination by NMR, that is analysis of multi-component mixture, elemental analysis, organic functional group analysis. Now coming to qualitative application. So NMR has a vast application for qualitative application. For qualitative application, we can find, suppose ethanol. If ethanol is there, ethanol contains three types of proton, that is CH3, CH2, OH. So that will produce three different peaks at three different chemical shift position. And similarly, this is the NMR spectra of pure acidified ethanol. So due to at high resolution, and this is at low resolution, because at low resolution no chemical split will be observed, but in case of high resolution, then chemical split will be observed. And this is the NMR spectra of highly purified ethanol under high resolution. And this is for methanol at different temperatures, that is a shifting of the peaks. And this is for benzyl alcohol. You know, for benzyl alcohol, three different types of peaks are there. Corresponding to that, you will get different three different types of protons are there, and correspondingly you will get three different peaks. Now, after we will discuss the next chapter, that is called mass spectrometry. Mass spectrometry. Now first we will discuss the theory of mass spectrometry. So we know that if we take a molecule and bombard it with a beam of highly energy electrons, then the molecule will undergo ionization. Taking the clue from the ionization of atoms to give the ions, you may be prompted to say that will ionize, and you are absolutely right. So this is what exactly done in the mass spectrometry. Here the molecule in the vapor phase is bomb. So in case of mass spectrometry, the principle lies here. So here the molecule in the vapor phase is bombarded with a beam of high energy, that is around 70 electron volt electrons. So these electrons knock off the electron from the molecule, leading to formation of a positively charged molecular ion M plus, and more appropriately, that is a radical ion or a radical cation. For example, if for example, the radical ion formation from the ammonia can be represented as, so here this is the ammonia molecule, and if ammonia molecule is bombarded with a beam of high energy electrons, then the electron from the ammonia molecule will be removed. So that will become radical cation or radical ion or molecular ion. So the radical ion obtained have large amount of extra energy, which is much more than that required to breaking the covalent bonds. Therefore, the highly energetic molecular ions undergo fragmentation, yielding smaller fragments. For example, so the ammonium radical ion become very unstable, so that will undergo fragmentation to form different types of fragments. So that may first undergo fragmentation to form NH2 plus and one hydrogen radical, hydrogen free radical, and similarly again this will undergo fragmentation to form NH plus radical with hydrogen radical, and after that again that will undergo fragmentation to form the nitrogen plus and H free radical. As the molecular ion can fragment in a number of ways depending upon the nature of the molecule, the fragments provide the clue to the structure of the molecule. The radical ion and the fragments obtained from the molecule are then separated according to their m by z value, where m is the mass and z is the charge of the ions, using the magnetic and or electrostatic fields. Now the record of the m by z value. So here m is the mass of the ion and z is the charge of the ion. So the record of the m by j value of these species against their relative amounts or intensity is known as mass spectrum of the sample. So this is a characteristic mass spectrum of methanol. So when methanol undergo bombardment with highly energetic electron, so that will undergo fragmentation to form different types of species. So here this is a typical mass spectrum of methanol molecule, showing as typical showing the formation of different fragments. The x-axis represent the x-axis of the spectrum represent the m by z value of the fragment ions, and the y-axis give the relative intensity or abundance of the different fragments. The y-axis intensity the y-axis for the for the y-axis, the intensity of the peak corresponding to the most abundant fragment, that is first that will convert it into CH2OH plus, and that is having m by z value 31, is arbitrarily assigned the intensity of 100%. So here this is the most abundant fragment, and that its intensity is arbitrarily assigned to 100%, and the peak intensity of the other ions generated due to further fragmentation process. The most intense peak is called a base peak, and it is not necessarily by the molecular ion peak, which is at m by z value 32. Now coming to the isotopic peak. The peak of m by z 33 in the case discussed above is an isotopic peak, and that is called m plus 1 cation radical peak. The origin of this peak can be understood if we take into account that the natural abundance of the isotope constituent atom of a molecule, And again, you know that most of the elements exist in nature predominantly as a single entity, as a collection of identical atoms. However, some element having the isotopes, they exist as a mixture of atoms having some atomic number but different mass number. For example, having same atomic number but different mass number. For example, carbon in nature exists as 6 carbon 12 as well as 6 carbon 13 atoms. And the abundance of 6 carbon 13 atom is around 1.1%, while that of the abundance of the 6 carbon 12 will be 98.9%. This measures that if we will have a thousands of carbon atoms, then there will be 11 atoms that would have 6 carbon. So, so if we will take thousands of carbon atoms, then 11 atoms will be 6 carbon 13 isotope, while 989 atoms will be having 6 carbon 12 isotope. So in case of the above example, it amounts to saying that for every 1000 molecules of methanol containing 6 carbon 12 isotope, it will be 11 methanol molecules having 6 carbon 13 atom. So these molecules would have a molecular mass of 33 gram per mole, assigned a normal value of 32. Hence, the peak of M by Z 33 will also be observed. So here you can see. So if we take the because we know that the methanol for the molecular mass is 32, but if we take 100 molecules of methanol, 989 molecules having molecular mass 32, while 11 molecules having molecular mass 33. So hence, a small peak of M by Z equal to 33 will be observed. Now coming to the instrument of the mass spectrometry. So the instrument, the components, the essential components of the mass spectrometer, that is the inlet device, ionization chamber or ion source, analyzer, detector and processing and output device. So this is the schematic diagram showing the component of a mass spectrometer. So this is the inlet of the sample under investigation. After that, that will enter into the ionization chamber where the sample under investigation in the vapor phase will bombarded with high energetic electrons, and that will convert it into ions. And after that, mass analyzer will be there that will show M by Z value, that will count the fragments having M by Z values, and that will be placed in the x-axis, and the y-axis will be its intensity according to the population. Now detection of ions, that is ion transducer, and after that signal processing unit that will show, and hence that will convert the output device. So these are the different parts. The first one is inlet device, then ionization chamber. Two types of ionization sources are there, that is gas phase source and resorption source. And the next one is analyzer. So two such type of analyzers are commonly employed in the mass spectrometer, that is magnetic sector analyzer and double focusing analyzer. So these are the different schematic diagrams of the magnetic sector mass analyzer, and the next one is that is the schematic diagram of a double focusing mass analyzer. Now coming to the detector or ion collector, and after that processing and output device. Now application of mass spectrometry. First one is qualitative application of the mass spectrometry. The most common qualitative applications are determination of molecular mass of the analyte, because the analyte is unknown. So from this we can determine the molecular mass. Now determination of molecular formula of the analyte, determination of structure of the analyte, and identification of the analyte. So these are the applications. You can go through the applications. And quantitative application of mass spectrometry. So besides the qualitative analysis, so the quantitative analysis is main aim of an analytical chemist. So mass spectrometry has an important role that it play achieving the subject and analytical chemist. It can be effectively used for the qualitative determination of alone in a complex system with a large number of components, especially in the case of petroleum, pharmaceuticals, and environmental samples. And after that, we will discuss some applications. So here, the unit 14, the unit 14 deals with structural elucidation by integrated spectroscopic methods. So whatever we have studied till now, based upon that spectroscopic methods, the structural elucidation of unknown analyte or unknown sample. So here first one is structural informations available from the different types of spectra. From the mass spectra, the M by Z value of the molecular ion, that is M plus radical, gives the molecular mass and can also be used for the gathering molecular formula, and the relative intensity of the M plus 1 cation radical and M plus 2 cation radical peaks can be related to the number and nature of the heteroatoms present in a molecule. The odd molecular mass is indicative of the presence of nitrogen atom in the molecule. However, these are to be further confirmed by other methods by analyzing the fragmentation patterns, typically nitrogen containing functional groups. The characteristics arises from the typical fragmentation patterns of various class of functional groups such as alpha cleavage, loss of small molecules for examples, removal of hydrogen, ethylene are quite useful. Certain peaks which may be attributed to the rearrangement of molecular ions or its fragment ions also give the significant structural leads. And here UV visible spectrometer spectrum, that is the application of UV visible spectrum that we have already discussed. After that, IR spectrum that we have also already discussed. So these are this table showing the different functional groups, the frequency range of the different functional groups of the organic compounds. And here NMR spectra. Now, structural elucidation of organic molecules. So here a compound having a molecular formula C3H3O showing the following spectra, deduce its structure. So here a mass spectra is given and its NMR, its IR spectra is given from, and its NMR spectra is given. From this both the three spectra, we have to find out the molecular the structure of the molecule or the structure of the analyte. You can easily go through all these examples. You can easily elucidate the structure of the analyte and molecular formula of the analyte also. So all these examples are here. Okay, so we'll stop now. Hello, hello, hello.